Yeah. Hey.
Do I look okay? You check. Am I in the picture?
Yeah, you
I'm
are.
Good? Okay.
Yeah.
Let's get started. Okay. All right. We're doing this makeup class. We're gonna do a new topic. So we have done 5 topics, right? We have the fundamental building blocks to build our discrete event simulation models. But from this topic on, until topic 9, we're gonna talk about advanced techniques to design a more efficient discrete event simulation experiment. So here, first of all, let's discuss topic 6, output analysis. Alright, so this is a quick outline. Output analysis for terminating systems and non-terminating systems. So we have seen both, actually. We have seen examples of both cases. So we have two types, right? So what is output analysis, right? We collect data, we provide an estimation at the end of the simulation. We're hoping to use our estimation to approximate some unknown factor, unknown quantity. Okay, but if you only give me one number, it makes no sense. I don't know how many simulations you did, and I don't know how accurate it is, right? So all the simulation, all meaningful simulation result comes with one number followed by plus minus. That's a confidence interval, right? That tells us how accurate it is and what is the error bound at an acceptable confidence level, such as 95%, right? So this is what this is about here. So we have 2 kinds of simulations. One is terminating system simulations, and the other one is non-terminating systems. For instance, the non-terminating system, it's a simulation, right? If you want to estimate the time it takes until a system eventually collapses, you don't know beforehand how long it will take, right, until the system collapses. For termination system, you have a criteria, you have a time, like T, big T. You're estimating the average queue length of a workshop, of a shop, then you know when to stop, right? So it's somewhat more difficult in the second case. If you have a terminating simulation, it's somewhat easy. Okay, so this is the outline. So we're going to talk about confidence interval for the estimation of expectation. What if you don't want to estimate expectation? What if you want to estimate variance? What if you want to estimate something else, like quantile, right? We'll talk about the other things briefly. So actually we're going to talk about a more general framework. The second bullet point here is confidence interval for smooth function of expectation. You will see what it means and you will see how useful it is later. Okay. Let's start with, let's briefly illustrate the terminating simulations. There's a natural event that specifies the length of the run, such as a day, such as, estimating the total waiting time for the first 500 customers. The 500 is the termination criteria, right? So this involves, answering questions about the system at specific times or specific number and estimating transient performance because we're terminating before steady state is reached, right? Okay. There's a non-terminating system as well. There's no natural event to specify the length of the run. Therefore, for instance, if you hope to estimate the steady state expected waiting time of customers, I mean, some of you took 760, you know what I mean by steady state, right? You send t to infinity, you have steady state. So how do you estimate steady state? You have to send t to a large number, but how large, right? Okay. So answering this question, or the steady state of expected cost of an inventory system, right? So recall that one example we gave in the previous topic is that estimating the total cost within a finite window. That's not that, right? That's sort of a first category. Answer this question about the system behavior in the long run, steady state behavior, and the system achieves steady state if, after a certain amount of time, it forgets about initial condition. So steady state really means, it's entirely loss of memory, and performance functions look like stationary, like time independent, right? Okay, we will talk about the first. Output analysis for terminating simulations. Alright, let's review confidence interval a little bit. Consider a simulation that terminates with some event E, some pre-specified termination criteria. Right. For instance, T, for instance, total number of departure, and that. We run n independent replications, independent samples, right? Then we can do Monte Carlo estimation, right? With all same initial condition, we can regard each sample as ID, right? Okay. like day 1, day 2, day 3 behavior. We're using the same initial condition, you can regard the outcome to be ID. Let xj be the random variable obtained from the jth run of the simulation. If the xj's are comparable, they refer to the same quantity, then they're treated as ID because you have an initial condition that is the same. For example, waiting time of the 10th customer in the queue, how do you estimate that? You start the queue using the same initial condition. We got C here. Yeah. If you sit closer to me, you can get into the picture.
Oh,
If that's what you want, okay. So we have new handouts. We just started. Okay. If the waiting time of if the mean waiting time of the 10th customer in the queue is something you want to estimate, what you need to do is to start the day with an initial condition, same initial condition, empty system, whatever, run this for n times, and get the 10th customer and estimate its waiting time. That's one sample, n times average, right? Treatment ID. Time it takes on a given day to finish servicing customers in a bank after it closes. Run many samples. Basically, the examples we have gone through in the previous topic were ideas about how to simulate one path, right? Sometimes you have to work on multiple paths. You have to have a for loop, right? Looping the sample. Amount of capital in an insurance company at time t, right? I mean, of course, this is estimated by one path, but what if I want mean of it? Okay, so here is a review of estimation of a mean. So let's say mu is equal to an expectation of x, and let's say mu is something you want to estimate. Of course, one x is easy, it's an easy, simple random variable, you compute it. But in many cases, x is not. Like, the total number of customer in the system by some time, you can't compute it. You have to estimate that average rate. Okay. A Monte Carlo estimator is really just sample mean, right? The supporting theorem for this, in order for this to be a good estimator, is draw law of large number. You know that when n is large enough, this is going to be good. But here we're going to talk about how large should n be and how to determine the relation between n, the sample size choice, and the accuracy level, right? So, right, so large is good enough, good, but how large, right? You don't have a limited simulation budget, right? You only have a finite budget, so how do you do it? All right, the approximate, this is something we derived earlier, 100 times 1 minus alpha %, so alpha is the fractional number. Count the interval for mu is given by this, right? When we say approximate, we mean, when n is large enough, this is behaving like normal, so we have a normal quantile appearing here, right? You have seen this derived earlier in topic 1, I think, right? So using this data, n sample, you are able to compute its average, sample mean, you're able to compute its sample variance, and you're using sample variance to approximate its variance. You don't know the true variance, sigma squared, in most of the time. You don't even know the mean, right? Okay? Then let's say your confidence level, you want to be this confident. Like alpha is 0.05, then this is going to be 95% confidence. Then this is it, right? So when you output this, when n is chosen, you're going to give a x bar plus minus some number, right? That's usually what it looks like, right? Sample mean is this, and the z means what, right? Z is the alpha quantile, or 1 minus alpha quantile. Implication, right? This. So, alright. So I'm still reviewing confidence interval and how it's derived. So here is how it's derived. I mean, this repeats what the earlier slide. Okay. Quick review of how it's derived. So we know that this guy converges to z because of a CLT central theorem. We know that this guy will be converging to the true variance as n increases, strong law of large number. So we modify the CLT by dividing, okay, let me see. Right, let me just directly go here, right? On the one hand, this thing is interpreted as an envelope, as an interval containing mu, right? So this guy less than z is nothing but this guy is smaller than the upper bound, less than the lower bound, which is plus minus. And moving things around, and you have a interval containing mu, and the interval is symmetric. Right? So the upper limit and lower limit are given here using the data. On the other hand, this guy, same guy, when n is large enough, can be approximated by a probability, given known probability in terms of normal. So all you need to do is to match the two to obtain common interval. So, and the common interval is given by this. Okay. So this is how it's proved, how it is proved. Here are the issues. Are the common intervals good enough? Meaning, is it small enough, right? For a fixed number of simulation run, let's say this is your simulation budget. We call it simulation budget because we want to interpret this as some kind of our computation resource. Like, I have this many machines, or I have this amount of time to run this machine, right? Common interval is constructed in a way, may or may not be small. You want small? A good common interval should allow us to approximate the true value of ex accurately, meaning ex falls into my interval with a high probability, close to 1, right? So I want the interval to be small. I want the probability to be big. It's a trade-off. If our estimator is large, say the mean value is large of some random variable, it's in general easy to obtain a common interval, which is reasonable. Because mean is really large, it's easy to just come up with a relatively small interval to sandwich it. But what if the estimator is small, like close to 0? It's a positive random variable whose mean is very, very small. Then it's possible, if you don't do well, if you don't have enough sample, you're going to have an interval that overlaps with the negative half-line, which does not make sense. Because this thing is positive, you can't have a common interval which has overlap with negative half-line. Right. We will talk more about this when we talk about this rare event simulation in the next two topics. So the question here is that what if we have a specific precision level? We quantify our precision level. We need to choose an n large enough for the common interval to a given precision level. Right? So there are two ways in general to measure precision: absolute error and relative error. Right? Let's see what is absolute error. Okay. So let's say we prescribe a absolute error, epsilon, which is less than is positive. Right? Some small number though, small. Find the required number of n such that the true value deviating from my estimator is less than epsilon with a probability that is big enough. Right? This is your confidence level. You can't guarantee this for sure, but you can put a probability there to measure the certainty, or say the confidence level, right? Because this guy is random, right? Okay. So now we're given this epsilon. So all you need to do, based on our understanding of CLT, is to let the half width to be less than epsilon, because this right hand side, if you do that, the right hand side is automatically satisfied. Okay. So this is the half width. You have the plus minus, right? Of course, this n, the solution to this equation would depend on alpha and epsilon, because you chose a big epsilon, you don't need many n, right? You choose a smaller alpha, it changes n as well. So I have a function n in terms of epsilon and alpha, right? Decreasing, there's a monotonicity relation between n and the parameters, right? All right, so this equation can be, transformed into this kind of solution. So moving things around and square both sides, you have n equals this guy divided by this epsilon. Just simple algebra, right? And n has to be integer, so let me take the seal of it to make sure it's strictly less than. What is the problem here? We seem to have found a formula to determine n. Is there any problem here? Is there a problem here? Is it good enough? How do you know n?
The standard arrow is depending on n.
You have n here, you have n here, right? This is not a closed form solution, right? This is some kind of equation that n has to solve, right? Right. Two approaches to solve the n. So again, right, let me make it clear. We're trying to solve n such that this kind of condition is satisfied. Okay? At least approximately satisfied, right? Okay. The first approach is the two-step approach, right? Run a pilot simulation. By pilot, we mean a small preparation phase. You know what it means, right? Sometimes before the main algorithm, we have to do a preparation phase. Run a pilot simulation with a small n, call that n prime, runs to estimate the variance. You sort of know its magnitude, and you estimate this first. Then do a new simulation, the main simulation, based on your estimation of this guy. Treat it as a constant. Then solve. Then you use this formula to determine what n you should do. This then will be the number of samples in your main simulation. Makes sense, right? I mean, because this guy will be accurate when n is large, and it converts pretty fast. So usually the n prime doesn't have to be very large, like 100 or something. But it's often the case that this true n, this n you use for your main simulation, can be as large as millions. So you want to have a better estimate of this. So you really have to do a good job in estimating the right hand side, and n prime need not to be too large in general, 100 or 50.
How do we know the 2 stages good enough? Maybe we need more stages, not more steps. Do
Yours-
line recursion.
You could. That's the approach too. Approach two is called the sequential stopping. So we define a stopping time and epsilon r. So can you just click over? Yeah. We have a 2-stage. So we had a 2-stage problem here, right? We could do a one-step problem called the sequential stopping problem, defining a stopping time n such that this condition is met. So we increase n, we check this. We increase n, we check it until the first time this condition is met. We just take that n. That's related to your question, right?
Yes.
So when we stop, we know that the condition is met. Are you good, right? But one thing to notice here, the condition is this. We add a term on the left-hand side to control the error. So, okay, why do we add a term like this? I mean, are we trying to be cautious? If you add a positive term here, obviously you need a bigger n here. So looks like you're too conservative, right? You're getting a bigger n. And this error term should be a small order term of the first term, because the first term is 1 over root n. The second order term cannot beat this term. It has to play a role when n is small, but it cannot be comparable to the first term. Why do we need it? Okay, how about this? Everything is random, right? Okay, what if I run 3 samples, n equals 3, then I see a 0 here? Is it possible? It's possible. I have x1, x2, x3.